Welcome back to the course on blockchain. So, we are discussing about this ByzCoin consensus mechanism. In the last class, we have looked into a little bit of background of a nice cryptographic signing mechanism called COSI or the collective signing, which ByzCoin uses for signing individual blocks. So, today we look into the details of this ByzCoin mechanism. About how ByzCoin work and how ByzCoin solves the problem which was there in case of Bitcoin and the Bitcoin NG protocol. And ByzCoin is a nice architecture in the sense that it combines the concept from proof of work and PBFT together, and it takes the good of both Bitcoin as well as Bitcoin NG, and by combining all these concepts all together, it designs a nice protocol, a nice mechanism for ensuring consensus in a blockchain based system. So, let us look into the ByzCoin in details. If you remember the requirement for a blockchain consensus protocol that I have mentioned in the last class, the first one is the Byzantine fault tolerant. The protocol need to be Byzantine fault tolerant. The second one is it should provide strong consistency guarantee. The third one is it should scale well to increasing workload, and the fourth one was it should scale well to increasing network size. Now, if you look into the ByzCoin protocol, the ByzCoin protocol will satisfy completely the first two requirements. That means, the protocol is Byzantine fault tolerant and it provides strong consistency guarantee by avoiding the forks. The second one, the third and fourth one, that two requirements, it makes a nice trade off between the performance in terms of the transaction that can be supported, transaction throughput that can be supported, and the scalability in terms of network size. This ByzCoin protocol, as I have mentioned, it takes the good for from Bitcoin as well as from Bitcoin NG and combines the concept of proof of work scalability and PBFT scalability altogether to increase the scalability in terms of number of nodes as well as in terms of number of transactions that can be supported. First let us look into some problems in Bitcoin which motivates behind the design of this ByzCoin protocol. So, in case of Bitcoin, there is no verifiable commitment of the system that a block would exist. So, for example, the probability of successful fork attack, what we have learned earlier, that it decreases as the size of the blockchain increases. So, whenever you have a large blockchain with a long chain, during that time you have the lower probability of having a fork attack. But whenever the blockchain is growing, at that time you always have a possibility of the fork attack, and the fork attack actually prevents some of the valid block to exist in blockchain. So, what happens that sometime it may happen that well earlier say this was your longest chain, and after having a fork it may happen that this red chain becomes the longest chain. So, in that case these two nodes, these two blue nodes which were there earlier, that they will be considered as a fork chain and they will not be used any further. So, that is why we say that in Bitcoin we do not have any verifiable commitment of the system. So, even if you have committed this block and this block seems to be a correct block, but there is no guarantee that this block will be a part of your final blockchain, and that way it will be a kind of waste of resources. So, because you know that Bitcoin anyway utilizes a significant amount of mining power, and depending on the system power and your computation efficiency, you are able to generate a mining block. Now, the thing is that you have utilized so much of resource in the system, but ultimately the block that you have generated, that block is useless because it has become a part of the fork. So, that is one major problem in Bitcoin, and in this case as I have mentioned that these two block becomes forked and they are not utilized any further. So, that was the problem with Bitcoin, and the problem with Bitcoin NG, as I was mentioning in the last class, that a faulty key block is verified only after the end of the round. So, a faulty miner, it can introduce a number of correct microblocks following a faulty microblock in the system. For example, in this case, this particular key block, it has been say introduced by a miner. So, this miner has introduced a number of correct microblocks followed by a faulty microblock. So, this before is a faulty microblock. So, in this particular case, you can detect that this miner which was here, which has generated this particular key block, it is a Byzantine miner or it is a malicious miner or a faulty miner only after it has generated this particular block. And the interesting thing is that by the time it has already added this block to this blockchain, because you have asked or you have voted, or better to say that the system has given the power to this miner to introduce new block in the system. So, that way the miner has already added the block, and after that you are verifying that that particular block is incorrect. So, that is the case. Now, a fork alleviates this problem further, because even if there is a fork, so it may happen certain forks are invalidated. So, at this stage, if it happens that another node creates a key block here that gets pointed here. So, all these valid blocks becomes invalid. So, we solve this problem by a set of PBFT verifiers. So, now that idea that we talked earlier, that before putting the block in the blockchain, rather than a single block or a single node or a single signer signing the block, you make a set of signer who will collectively signing the block. So, that is the solution we are introducing here, that you solve this problem by a set of PBFT verifier who will verify a block, and then only the block is added in the blockchain. That means, we are not giving the power to a single miner to introduce multiple microblocks one after another, although that miner will be the leader of the system, but a set of witness which will apply this collective signing protocol that I have discussed in the last class. They will apply the collective signing protocol, and after applying the collective signing protocol, if that particular microblock is verified by multiple such cosigners, then only that will get added in the blockchain. So, in this case, if you look into the earlier problem, this block before, it will never get added in this blockchain, and at this stage, because other signers, they will detect that, well, see, this miner is faulty. So, remove this miner and add up a new miner by introducing the proof of work mechanism to introduce another new key block in the system. So, that way you can resolve this particular problem in case of blockchain consensus. Well, so let us look into this solution of this in details, that how you can use PBFT in this case. So, in that ByzCoin paper, initially they have discussed about a Strawman design, which they call as the PBFT coin. In PBFT coin, their assumption is standard to the normal PBFT system, that you have 3f plus 1 fixed trustees who are there, who will run the PBFT to withstand f number of failures. So, to sustain f number of failures, as we have looked into the concept of PBFT, that you require 3f plus 1 number of nodes in the system. So, the same thing is used here. So, this avoids the probabilistic strong consistency by introducing low latency in the system. So, why? Because say whenever you have multiple signers who are signing a block, and then only you are adding a block in the system. So, when multiple signer is signing a new block, during that time, well, if there is another block which is being created by another side of the node, it is more likely that, well, this signing will take some time, and by that time one block will propagate in the entire network. So, that way it avoids this probabilistic strong consistency, that, well, now among the set of miners who are there in the world, whenever a new block is being proposed, then those miners in the world, they are collectively voting for only one block, and that particular block is getting added in your system. So that way you can avoid this forking in the system. So this entire concept, so let me try to explain it again with the help of one example. So the idea is there, you have now multiple nodes in the network who are connected with each other. Say these are multiple nodes in the network, they are assumed that they are connected with each other through some means, and now among them some of the nodes are working as miners. So, we have these nodes and then some of the nodes we are designated as miners. So, the node where I am writing as M, they are the miners in the system. Now, in case of the earlier case, it may happen that well this miner is trying to validate a new block or create a new block by using the proof of work mechanism. At the same time, this miner is trying to create a new block. So, that way if both of them are able to successfully mine a new block at the same time, then you have two different blocks which are pointing to the same parent block in case of blockchain. So, now one miner is pointing to this block. So, this was the previous block, another is pointing the block. So, I am just naming them as M1 and M2. So, M1 has created this block and M2 has created this block, and both are valid block pointing to the same parent block. So, that is why we have the problem of this strong consistency here, that well we are generating certain blocks which can result in a fork in the system. Now, whenever in case of this particular case, what you are doing, you are running a PBFT among these miners. So, out of these miners you are taking certain miners who are, so these are the miners which I have marked as circle. So, these are the miners, say let us use a different color. So, these are the miners who are authorized to sign the block. So, we are applying this kind of collective signing concept. Now, these miners, now they will run a PBFT protocol among themselves. So, these miners create another level of hierarchy. So, they will run the PBFT among themselves to add up a new block in the system. So, that way every time you are making a consensus among the miners that which block is going to add in the system, and that way you are preventing multiple blocks to get added to the blockchain at the same time, and that way you are preventing the fork to be happening, and which in turn gives you a strong consistency support in the system. Well, so that is the broad idea here, that we are avoiding the forks in the system. So, these blocks they are added only after verification from the trustees. So, here these are the set of nodes who are working as the miners, and these miners are arranged as a set of which we call as a set of trustees who collectively decides that which particular block need to be added to the system, and that particular block is only added to the existing blockchain. Okay. So, that was the solution using PBFT. Now, let us see the problem here. So, we have certain problems of PBFT which are there, which we need to tackle in this particular scenario. So, the first problem is that PBFT requires a static consensus group. Now, in case of a proof of work based system, we do not want a static consensus group. Why? Because it is an open environment and anyone can join as a miner. Now, say today I am joining as a miner, if there is a static consensus group, then what is the guarantee or when I will get the chance to join to that particular consensus group. So, our basic idea that the system will behave like a open environment in case of proof of work, what we call as a permissionless blockchain. That concept of permissionless blockchain gets void if you are thinking about a static consensus group. So, that is one of the major limitation for this PBFT type of protocol. Now, this PBFT type of protocol, because of it works on this message passing architecture, it uses a static consensus group, and scalability in terms of number of nodes, it is also a problem, because PBFT it uses O of n square communication complexity and O of n verification complexity. So, if you remember the PBFT mechanism that every node in the prepare and the commit phase, every node need to send the messages to all other nodes in that closed consensus group, and they will get that message and only then they will be able to verify it. So, that way your communication complexity is now O of n square, and the verification complexity of is O of n because that particular statement or the particular block need to be verified by all the nodes in the system. So, that is the two major things, and the third problem in PBFT is that you do not have a third party verifiable proof. That means, if you remember PBFT uses message authentication code. So, in case of message authentication code, you have shared secret between any two pair of nodes. If you have shared secret between any two pair of nodes, that means if you have some 1000 miners in the system, then every pair of nodes, every pair of miner need to have a shared secret among themselves, which is a overhead obviously for the entire system, and which prevents the system to behave like a open system. And another problem which can be there in case of PBFT is the Sybil attack. Now, in case of Sybil attack, a node it can create multiple pseudonymous identities. So, the node can create multiple such identities to subvert the 3a+1 requirement of PBFT. So, that means assume that a malicious node, there is a malicious node, and that malicious node creates some 100 different identities which apparently looks different. So, if you are getting the message from those nodes and that Sybil attack becomes prominent even if you are using an open environment where any malicious node can join in the system and can then subvert the entire system by applying this kind of Sybil attack by false identities, multiple false identities simultaneously. So, to the other node it just looks like that it is receiving the message from 1000 other nodes, but actually those 1000 other nodes are pointing to a single malicious node. So, that is the kind of Sybil attack which can happen in case of this kind of PBFT based consensus groups. Now, to solve this, our first target would be to open the consensus group. So, how will you open the consensus group? To open the consensus group, we use the proof of work based system. So, we now use the proof of work based system to give a proof of membership of a miner as a part of the trustee. That means, we utilize proof of work to determine who will be getting a membership in the trustee board or in the group of trustee. So, I will explain that with the help of a diagram, but before going to that, this particular architecture it maintain a balance of power within the BFT consensus group. So, how it maintains this balance of power? So, it uses a fixed size sliding window. Each time a miner finds a new block, it receives a consensus group share, and this share provides the miner's membership in the trustee group. So, let us look into an example to make the thing much clear. So, here this is the sliding window, this is my current window where I am considering that which are the miners who will be there in the trustee group. Now, here we see that well this particular miner it has mined these two blocks, then this particular miner it has mined 3 blocks, and this particular miner it has mined 2 blocks. So, within this window, so here the window size is 1, 2, 3, 4, 5, 6, 7 with this window size of 7. So, it gets the share of 2, this gets the share of 3, this node gets the share of 2. So, this is their voting power or the power to participate in the set of or the group of trustees. So, in this particular window, who are the in the last window, who has mined the maximum number of blocks, they become the part of the trustee group to vote further or to sign further about the validity of a particular block. Now, here whenever you are generating a block, say after this whenever a new block will be generated, this new block obviously will be generated by this leader here written as L, but this block need to be collectively signed by this leader along with all these 2 signers who are there and who are the part of the miner. So, that way we are distributing this entire power among a set of trustees, and at the same time we are preventing inactive miner to be there in the part of this trustee group. So, if you put a inactive miner in that set of trustee group, you have a question about the validity of that miner, because that miner has not proven enough or given a proof that it can sufficiently or it has the sufficient resource or sufficient motivation to generate a new block in the system. Well, so that is the idea of opening the consensus group. Now, your consensus group is not limited to a set of miners, rather dynamically based on the miners who are generating the blocks and their share in the current window, you are deciding that which miners will be part of this witness group who will be signing a new block. Well, then the second thing is our problem was with the message authentication code. So, because the message authentication code used private key cryptography, you need a shared secret between any 2 pair of the miners. Now, here we are utilizing the COSI protocol. So, you substitute the MAC with public key cryptography. You can utilize this elliptic curve based cryptography or ECDSA mechanism to provide more efficiency, say to use the BLS, you can use NOR multi-signature or to have a more scalability in the COSI architecture, in the tree based architecture, you can use BLS based encryption. So, it is third party verifiable, you have a public key. So, once every node has the public key, now in the key block, rather than putting the public key of just the leader, along with that you also put the public key of all the witnesses who has signed those blocks. So, now if you remember in the Bitcoin NG key block structure, so in the Bitcoin NG key block you had the key of the leader. Now, apart from the key of the leader, you also add up the key of all the witnesses, say W1, W2, W3 who has collectively signed the block. And here you can use a specific topology like ring, chain, this kind of topology for the collective verification. Say if these miners are arranged in a chain kind of topology, then during the verification you can pass that particular block to these miners. So, say they have signed, so you had this block B in the collective signing, say if it is first encrypted by or signed by say KL, then it has been signed by KW1, then it has been signed by KW2. If that is the case, then in a reverse order you can just keep on checking the verification. But we can again apply the concept of COSI here to have a scalable approach of verification. So, let us see how. So, how we are improving efficiency using COSI? First of all, for the communication complexity, your standard PBFT protocol was O of n square communication complexity. Now, we are thinking of, well, even if we are going a linear complexity by utilizing this chain based system, can I improve the complexity further? And the answer is yes, you can do it using the tree based multicast protocol which has been utilized in COSI. So, you can share the information in the tree with O of log n message complexity. And then for the verification, you can use this NOR multi-signature or the BLS for verification, where you have a way of combining all the keys together, all the public keys together and get a final public key. So, if you remember the BLS encryption, if g to the power x and g to the power y are the public key, then from there you can generate the combined public key as g to the power x y. So, with the help of this combined public key, you can directly verify the message without going for this chaining procedure that I have explained just a couple of minutes before. And with this combined verification with the message complexity of O of n, O of 1 with a constant message complexity or constant complexity, you can verify the signature. Now, this multi-signature and the communication tree together, it uses this COSI protocol, and this COSI gives you a scalable way of doing the signing, performing the signing with O of log n complexity and verify the sign with O of 1 complexity. Now, if you just remember the key block, so let me go to this ByzCoin NG architecture. Well, before going to that, as we have mentioned earlier that this COSI, in COSI protocol you can implement PBFT with 2 subsequent COSI rounds with prepare and commit. So, if you remember the COSI description that we discussed in the last class, that in the first round, so every round has 2 phases, one downward phase and one upward phase. In the downward phase of first round, the leader it shares the statement to all the nodes, that means my S, and in the upward phase of the first round, everyone generates these values, individual values and the combined keys at every round. So, here these nodes generate their own key, share the public key with one computes the combined public key. So, that way these combined keys are created. In the third in the downward phase of the second round, that means in the phase 3, the leader sends a challenge by using this combined value and the corresponding block statement that you want to validate, that gets propagated, and in the final phase, that means the upward phase of the second round, you are generating these individual signatures with the help of R and Cs. So, that way you are emulating this behavior of PBFT using the 2 rounds of COSI protocol. Now, as I have mentioned, it also takes the good thing from ByzCoin NG. So, ByzCoin also uses the ByzCoin NG's idea of separating out the transaction verification and leader election. So, here again you have the key blocks and the micro blocks, and individual key block. Now, the difference is here. Earlier these individual key blocks they were containing the key of only one node or only one miner. Now, rather than having the key of only one miner, you have the combined key of all these nodes which are collectively signing all the micro blocks which are there. Now, say in different rounds, different ByzCoin NG round, or here I will say the ByzCoin round, at every round you say these are the individual rounds. Now, at every round among this set of miners, one node becomes the leader. So, if I consider this round, in this round this node has become the leader L, this yellow node has become the leader L, and it has generated these 2 micro blocks, and both of these micro blocks are now collectively signed by these 3 miners who are the part of this witness committee. Now, in the key block, rather than putting the key of this node, you are, so if you are using a BLS signature, in the earlier case you have put just the key of, say, the key of this node is g to the power x, the key of this node is g to the power y, and the key of this node is g to the power z. Now, in this key block you are putting the combined public key. If you are using BLS, you are putting the combined public key which is g to the power x y z. Now, using this key everyone can verify that, and whenever a micro block is generated by utilizing this tree based structure, you are verifying you are getting this micro block verified by these witnesses who are there among the miner, and then only adding the micro block in the blockchain. So, that way it solves the entire problem of ByzCoin NG as well as the standard ByzCoin. Okay. So, let us look into the performance aspect. So, in the performance aspect, this shows the block signing latency. So, here if you look into this line, so this is the line corresponds to ByzCoin. So, if you look into this line is, as you increase the block size, this line is less than the other protocol. So, this is the standard COSI or the flat COSI, that means it is not utilizing the tree based structure, rather the flat structure. In O of n it is performing the verification, and O of n square it is performing the signing. Here it is done by the tree based protocol, and this particular line corresponds to the standard PBFT protocol. So, you can see that it is significantly reducing the block commitment latency as you are increasing the block size. The second thing, if you look into the transaction per second, which was our major concern. So, if you look into this ByzCoin performance of transaction per second, so these particular lines, these two lines, they shows the transaction per second for ByzCoin with different numbers of miners, and this is the standard COSI protocol, and this is the Bitcoin protocol, the standard proof of work. So, you can see that well this ByzCoin, it is significantly able to improve the transaction per second, which is supported by the consensus protocol. So, for Bitcoin, the standard block size that they have considered up to 8 MB, which is now standard for proof of work based protocol. You can go up to 8 MB of block size. Now, if you increase the block size further, you can get around, say, if you think about the PayPal, which is a standard transaction platform. So, PayPal supports around 500 transactions per second. So, with ByzCoin you can reach up to that scale with block size of 16 MB or 32 MB. So, that way we see that well ByzCoin was able to significantly improve the performance in terms of transaction per second that can be supported in the system, and because it is a proof of work based protocol, again you can support large number of nodes, or it can work on top of large number of nodes. Okay. So, that is about the ByzCoin protocol. Two interesting things that I want to share with you. So, this particular the first reference it provides the original paper of ByzCoin. So, the original talk from the authors of that papers are also available there. So, I suggest all of you to go through that, and you also have the ByzCoin source publicly available. So, you can run a ByzCoin network and look into the different performance aspect of ByzCoin by exploring that particular architecture. That is all about ByzCoin. In the next class, we will further discuss about some of the other protocols which recently people or the researchers have developed to tackle the this scalability problem in blockchain based network. Thank you all for attending this course.